Maybe I should turn off the lights in front. Well, for some years now, it's been known that Donaldson theory can be interpreted in terms of a certain n equals 2 supersymmetric quantum field theory in 4 dimensions. And the question, therefore, has arisen of whether this is actually useful. So, when I first thought about this problem in the late 80s, partly in collaboration with my student Scott Axelrod, well, we tried to cut and paste and sum over physical states. But for Donaldson theory, such methods have been extensively developed, starting with Floor, and after a long peregrination, we eventually concluded that we could learn nothing essentially new. Well, there's another quite different approach, which seemed impractical at the time, but which led to developments that I'll explain now. So in this approach, we consider a four-manifold X. Now, just as in Donaldson theory, this quantum field theory needs a choice of Riemannian metric on X. Then you prove that certain objects are independent of the metric, and they are therefore invariants of the smooth structure of X, which I will somewhat crudely call topological invariance of X, but the term is a misnomer in this context, as most of you know. So, but here we'll consider not a single metric on X, rather we'll fix a metric G0, and we'll consider a one-parameter family of metrics, G sub t, which is t times G0, where t is a parameter, a real parameter that goes from 0 to infinity. Now, saying that that's what we're going to do may sound strange to people who work on classical Donaldson theory, because classical Donaldson theory is based on classical nonlinear partial differential equations, which are conformally invariant. And therefore, this deformation would do nothing in classical Donaldson theory. But even though the quantum field theory is formally associated with those conformally invariant equations, it is associated with it by a limiting process in which conformal invariance is lost. So, in the quantum theory, unlike the classical theory, this deformation does something. The question is what it does. Well, one fundamental statement, which comes from asymptotic freedom, and is one of the foundation stones for our understanding of the theory of nuclear forces and lots of other things in physics, is that for t going to 0, the behavior is controlled by weak coupling, and in particular, for t goes to 0, you can calculate explicitly and recover Donaldson's definitions. The statement that this is what happens for t goes to 0 is really the basis of the assertion that this theory is equivalent to Donaldson theory. The argument in my paper of 7 or so years ago was not phrased in precisely this language, but was very close. Well, if you could determine the behavior when t goes to infinity, you might get a new perspective on Donaldson theory. Well, the trouble with that, and the reason it for some years wasn't pursued, was that this was analogous to well-known unsolved problems in physics, like explaining quark confinement in the theory of nuclear forces. However, in the last couple of years, Natty Seiberg revived some of those questions in the supersymmetric case and started to make a lot of progress on it. And Natty and I collaborated on this case and were able to understand precisely in this problem what happens for large t. So we got a model of quark confinement actually, but we also got a description that has as a corollary a new approach to Donaldson theory. I might say that, of this whole development of the last couple of years, this is perhaps the aspect that's interested mathematicians the most, but it's part of a whole development of understanding the dynamics of supersymmetric theories with many other interesting things both before and afterwards, some of which, in my opinion, are even richer as regards the physics. Well, since I can't really explain the basic phenomenon because of not presuming the necessary background in quantum field theory, I'll instead just give two analogies. One will be mathematical and one will be physical. Well, the mathematical analogy involves the heat kernel proof of the index theorem. So here we have a Dirac operator D, and then the Hamiltonian is d squared. And then we consider a trace of the heat kernel at time t, Euclidean time t, not the ordinary trace. The trace for one type of spinor minus the trace for the other type of spinor. Minus 1 to the f is the operator that's 1 or minus 1 for the two kinds of spinors. And then one proves that this object is independent of t, and one finds two ways of calculating it. For t goes to 0, you use the short time behavior of the heat kernel, and you get a cohomological formula. And for t goes to infinity, you look at the zeros of the Hamiltonian, the physical states, the physical ground states, and you get the description as the index of the operator. So the statement that these two are equivalent is the index theorem. Something calculated by knowledge of the physics is equivalent to a cohomological formula. Of course, historically, in the case of the index problem, this was regarded as the question, and this was regarded as the answer. In Donaldson theory, the shoe was on the other foot, in the sense that Donaldson's definition involved a kind of cohomological formula, intersections on moduli spaces. So the question was posed here, and the answer, which involves a knowledge of the physics, is at large times. Now, the analogy between them is more precise than I've said. It's not just that you have a parameter t in both problems. When physicists look at the index problem, you've got a target space x, and you're doing elliptic operators on x. But the way we do elliptic operators on x is that we consider paths on x. So here, really, we've got a circle. And we look at maps of the circle into x. And the circle has to be endowed with a Riemannian metric, as is the target. But in one dimension, the classification of Riemannian metrics is a little simple. The circumference, which is the time, is the only invariant. So our one-parameter family of deformations sees all metrics in one dimension, while in 4 dimensions it's just a particular one-parameter family. And then this heat kernel proof would be interpreted by physicists in terms of a path integral definition of that expression and a proof by integration by parts on the function space, on the loop space, that it's independent of t, and then 2 different computations for large t or small t. So t, in the physical interpretation, plays the role, precisely the role we have. There's a circle there, which has a Riemannian metric, which is being scaled up precisely by multiplication by parameter t. Of course, you might ask, if the circle is really there, why is it that people who often do elliptic operators without talking about it? Well, I'd submit that's because the classification of one manifolds is so simple that much of mathematics is done suppressing the one. But when you get up to higher dimensions, where topology becomes more interesting, you can't suppress the truth about the role of path integrals anymore. Pardon the slightly smart alecky comment. So this is my mathematical analogy. Now I'll give a physical analogy, which will be many-body physics. So, of course, there are 2 branches. Well, okay, for our analogy, put a collection of atoms in a box. For instance, they might be atoms of lead, and we put them in a box at very low temperatures, and we want to know what they do. Now, let's suppose this is a well-posed problem in the mathematical sense. That means we know the basic laws governing the system. That means, for example, that we have a well-defined differential equation describing the system. Well, knowing how to write a well-defined differential equation governing a system means, pretty much by definition, that you know the behavior for small time. If you can also determine the behavior for large time, you say you've solved the problem. For instance, in the case of lead, when you throw the lead atoms in a box, the answer is that it becomes superconducting, the temperature being low. But superconductivity is a concept that can only be formulated, calculated, or measured by thinking about large times. So in general, in physics, in areas where the laws are known, the question is posed at short times by writing down some well-defined problem, and if you can also determine what happens for large times, you say you've solved the problem. By the way, here I've assumed we had a well-defined problem in the mathematical sense, but physics isn't always like that. So let's consider the opposite case, where the problem isn't well posed because the laws aren't known, and the goal is to discover the laws. In areas of physics that have that characteristic, you do experiments from which you want to infer the laws. Well, experiments by their nature measure what happens at large times, large enough times, so that the experimentalists manage to make their measurements. But in practice, those are large times indeed. And in that case, solving the problem is said to be determining the basic laws. But as I told you, the basic laws are, by definition, what happens at short times. So in physics, either you know what happens at short times since you know the basic laws, and the question is to solve the problem, that is to determine what happens at large times. Or conversely, you're doing experiments measuring what happens at large times, and the goal is to determine what happens at short times, that is to discover the basic laws. So, just as in my two examples of the index theorem and Donaldson theory, mathematicians might start at one end or the other, and likewise, basically, physics has to do with starting at one end of this or the other and trying to figure out the other end. Although which end you start at and which end you end at are quite different, depending on whether the goal of the operation is to discover laws that are not yet known, or to use them in a not yet understood situation. More or less, all of physics deals with one or the other of those two cases. So, Donaldson theory was defined by Donaldson at small times. It was analogous to a physics problem that was well posed but not yet answered. And Seiberg and I determined the behavior of the quantum field theory at large times. That is, we solved the physics problem that's equivalent to Donaldson theory. Or more exactly, it's not equivalent, but it has Donaldson theory as one of its manifestations. So, in this case, it's not just that we solved it, but the solution turned out to be very surprising. The light particles that an experimentalist would actually discover, if Donaldson theory were the theory of nature, so to speak, were not the ones that you wrote in the elementary Lagrangian. Magnetic monopoles became massless, and all kinds of strange things happened. And because the answer to the physics question was so surprising, its corollary for Donaldson theory is perhaps also surprising. This is what I will now explain. It involves an abelian gauge theory with monopoles that's equivalent for topological computations to the non-abelian gauge theory without monopoles that was used by Donaldson. So here we have a system of nonlinear equations, but with an abelian gauge group. So, for instance, if X is spin, X is a four-manifold. If X is spin, we take a complex line bundle L over X, and we let capital A be a connection on L. And then we've got the two spin bundles, say S plus and S minus, which are complex bundles of rank 2. If X isn't spin, then we combine the spin bundle and L into a spin C structure. But I think I will take the small liberty of not explaining that precisely right now. Then the data in the problem are a connection on L and the monopole field, which is a section of S plus tensored with L. Well, what equations are we going to write for this data? Well, in 4 dimensions, I'll use in general the name lambda p for the space of p-forms. But in 4 dimensions on a Riemannian manifold, the space lambda 2 has a natural decomposition in lambda 2 plus plus lambda 2 minus, where the two spaces are the eigenspaces of the Hodge star operator. And then the curvature of a connection, well, here since we're in the abelian situation, the curvature lacks its usual non-linear term. But in any event, the curvature is a 2 form, It's now an ordinary 2 form because the group is abelian. In Donaldson theory, the curvature with the Lie algebra value 2 form. Here the curvature is an ordinary 2 form, which we can project into the 2 eigenspaces. So we let f plus or minus be its projections, and the self-dual Yang-Mills equations, studied originally in physics by Polyakov and his collaborators, and in its mathematical applications by Donaldson and many others, the self-dual Yang-Mills equations would be the equations f plus equals 0. Well, the monopole equations are instead as follows. First of all, the structure group of the spin bundle in 4 dimensions is SU2. And as the 2-dimensional representation of SU2 is a pseudo-real or symplectic representation, SU2 being the same as SP1, the complex conjugate of S plus is S plus itself, S plus again. Now, if the monopole field M lies in S plus tensor L, then its complex conjugate lies in S plus bar tensor L inverse. I've identified L bar with L inverse using the unitary structure on L, which I may have neglected to mention. The connection was a unitary connection on this line bundle. So the L's cancel out, and using the fact that S plus bar is S plus again, M tensor S M bar takes values in S plus tensor itself. Well, in 4 dimensions, S plus tensor itself is the space of 0 forms plus 2 plus forms. So in particular, M tensor M bar has a projection to lambda 2 plus, which I'll simply call MM bar plus. Notice that MM bar plus lives in the same place as F plus. And now we can write our equations. The equations say that F plus is MM bar plus, and that M obeys the Dirac equations. Well, what kind of properties would you like such equations to have? You'd certainly like them to be elliptic, or more precisely, elliptic modulo the gauge transformations. The gauge invariance of the equations makes it impossible for them to be elliptic in the naive sense. Rather, if you look at the linearization, little t, of these equations around a solution, you see, what does it map? Well, a connection isn't quite a 1 form, but a displacement of a connection is a 1 form. And M lies in a linear space whose its displacement lies in the same space. The equations map us to a 2 plus form, and also to a section of S minus tensor L. Since the Dirac operator maps one spin bundle to the other, S plus goes to S minus. Anyway, the linearization is a little elliptic operator like that. It can't be elliptic because of gauge invariance, but rather it's part of an elliptic complex, where S represents the infinitesimal action of the gauge transformations. You see, since the gauge group is abelian, a generator of gauge transformations is simply a function, or an element of lambda 0, and little s is the operator that says how the data changes under an infinitesimal gauge transformation generated by some function. So we get this nice little elliptic complex, and its cohomology here is the space of solutions of the linearized equations modulo the gauge transformations, or in other words, the tangent space to the moduli space of solutions. Well, if we want to predict that dimension, if all is well, that's the same as the index of the complex, or in other words, the index of this elliptic operator. However, as the moduli spaces are simply real manifolds in general, we calculate the dimension, and therefore we need the index as a real operator, and that will give the dimension of the moduli space of solution, curly M, of solutions of the equations modulo gauge transformations. Well, this index we can calculate very quickly, because these equations are coupled, but just for calculating the index, we can deform them, and if we just drop this 0th order term from the equations, we would put the linearization in a more elementary form. The linearization, just t, capital T, the elliptic operator capital T, then just deforms to a sum of standard operators, one of which is the Dirac operator, and the other is the d plus d star operator, acting now on ordinary differential forms. No Lie algebra value because the gauge group is abelian. Ordinary differential forms that are projected onto the self-dual part. So the index is the index of this operator. Well, the only subtlety is that what's usually called the index of the Dirac operator is its index as a complex operator. Here we multiply by 2 because we must think of it as a real operator. And then we get a formula from the index theorem for the index of t. Well, one simple corollary of this is that generically, essentially, to simplify slightly, the dimension of the moduli space of solutions should be this number. And if that number is negative, after a generic perturbation, there won't be any solutions. So we can throw away more or less half the line bundles. If the index is negative, then the equations generically have no solutions on a fixed Four-Manifold and can give no topological information. By the way, as an aside, I said on a fixed Four-Manifold. If, for instance, this number were -1, then in a one-parameter family of Four-Manifolds you could find a solution. And you'd get a one-parameter family of Four-Manifolds by taking a Four-Manifold with a diffeomorphism and making a bundle over a circle. So you might still do something of interest when this number is negative, but you won't simply find topological invariance of a fixed Four-Manifold. So for today at least, we'll throw away those line bundles. Well, something nice happens to us, which is that another simple argument lets you throw away almost all the other line bundles, because you get a second inequality that goes in the opposite direction. So here, well, if I let capital A and capital B be the two equations, then the L2 norm of A squared plus B squared, what you might call mathematically the Witten formula, comes out. So we've reduced the story to that finite set of interesting line bundles. Well, to pursue farther, I'll make a simplifying assumption, which turns out to be equivalent to what Kronheimer and Ravka call simple type. It'll lead to some minor simplifications in what I'll say. It also happens to be an assumption that's true for all known Four-Manifolds. Although, well, it happens to be an assumption that loses nothing essential for all known Four-Manifolds, although it isn't understood if that's true for all Four-Manifolds. But for simplicity, if we consider a line bundle L that actually saturates our first inequality, that means that the expected dimension of the moduli space of solutions is 0. So generically, the moduli space of solutions of these equations consists of a finite set of points. Well, roughly what we want to do is, imitating one of Donaldson's original definitions, to define an invariant of the smooth structure of X by counting the solutions. X is a Four-Manifold. We pick one of those line bundles. The equation should have finitely many solutions after making some generic perturbation, and we want to count them. However, it's a fact of life that even high schoolers learn that the number of solutions of an equation isn't invariant under deformations. If X is a real variable, and we look at the equation x squared minus a equals 0, a being a real number, of course the number of solutions jumps from 2 to 0 when a changes sign. Here's what the picture looks like when a is positive. But we all know also what the cure for that is. You have to count the solutions with sign. If we call this expression f, we weight a solution by the sign of df dx. But df dx is the linearization of the equation. That's what we call t. So we need to weight a solution by the sign of the determinant of t. And then we count solutions with signs. As I just said, a solution should be weighted by the sign of the corresponding determinant. Well, for this to make sense, we need to be able to make sense of the sign of the determinant of t. To physicists, that involves the cancellation of a certain global anomaly, while mathematicians would describe it by saying that that's possible if what's called the determinant line of t is orientable. That's true here because we're studying t as a real operator, so we mean its determinant line in the real sense, and without changing the determinant line, we can deform t to the direct sum of this fixed operator, and this fixed operator has a determinant line that just floats in empty space. It's just a fixed line. This operator is independent of the data, so it has a determinant line that just sits there once and for all. And then d is naturally a complex operator that would have a complex determinant line, but today we're studying d as a real operator. And since a complex line is naturally orientable with an orientation given by multiplication by I, once you pick I as opposed to minus I, you have not just it's orientable, but you have a natural orientation of the determinant line. So not just is the determinant line orientable, but we get a natural orientation for all line bundles. Once we've picked an orientation, Donaldson's results about orientations of instanton moduli spaces, where not only they were orientable, but a choice of orientation depended on the same data. This is an aspect of the relation between the two theories. Now, you need orientability so that the determinant line makes sense, but you need a couple of other things in order to get an invariant by counting the solutions. Essentially, you need two things. Compactness, that solutions can't go to infinity. And secondly, well, ideally you would have a free action of the gauge group so that the quotient of the space of all data by the gauge group would be a smooth manifold. But if you can't quite have that, you at least want the solutions to keep away from any place where the gauge group fails to act freely. Well, as Moravko will perhaps explain in his talk better than I could, the first point follows from these positivity properties, which the Lagrangian is so nice and positive that nothing can go to infinity. And as for the second point, you see, the second point, which was a free action of the gauge group on the space of solutions, can only fail. Well, the gauge transformations act in a very elementary way, just by phase rotations of M. So the gauge group can fail to act freely only if M vanishes. M has to vanish identically, or it can't vanish in any open set by elliptic properties. So the only place where the gauge group can fail to act freely are the trivial solutions where M is 0. And then one shows by a simple argument, again analogous to an old argument of Donaldson's, that these exceptional singular solutions can be neglected if what's called B2 plus is bigger than 1. B2 plus is the dimension of the space of harmonic self-dual two-forms. If B2 plus is 1 or 0, you get a more elaborate story that we perhaps won't go into now. In short, if B2 plus is bigger than 1, then for every line bundle obeying this property, we define an invariant of the smooth structure as the sum of all solutions of the equations, with each solution weighted by the sign of the determinant of t. Well, this construction makes sense on its own and could well have been formulated independent of any knowledge of its relation to Donaldson theory. But in view of the way it materialized, it has a relation to Donaldson theory, which I shall now explain. Let X be minus twice the first Chern class of L. This definition doesn't quite mean that X is divisible by 2, because at the beginning I really only gave the definition for spin manifolds. And had we not had a spin manifold, for such spin manifolds, C1 of L is an integral class and X is divisible by 2. But had we not had a spin manifold, the definition at the beginning should have been slightly more subtle, and then we still would have defined X, but instead of being twice something else, it would have simply stood on its own feet. And we'd have learned in general, what I'll write at the bottom here, that X is congruent to W2 mod 2. So for a spin manifold, W2 vanishes, and X is 0 mod 2. So, since we found a certain basic set of line bundles, or really spin C structures, if we were more precise, we've gotten a distinguished set of integral cohomology classes, X, defined this way. I put in the minus sign in an attempt, which I hope was successful, to agree with the conventions of the work of a couple years ago of Kronheimer and Moravka. Well, also in relation to other formulas. So, we've defined certain x's that obey two properties. X squared is 2 chi plus 3 tau, and X is congruent to W2 mod 2. These properties may be familiar because if we happen to be on a Kähler manifold, then the canonical class of a Kähler manifold is a class that obeys these properties. Anyway, we've arrived at a certain distinguished set of cohomology classes that obey these properties, and the relation to Donaldson theory should be that these are the basic classes of Kronheimer and Moravka, which were classes that they proved to be finite in number. They proved to obey the second and conjectured to obey the first. Now, the main relation to the basic classes is the following, and this will also be the main statement of how this story is related to Donaldson theory. Well, the Donaldson invariants were organized by Kronheimer and Moravka as a function on the second cohomology. See, Donaldson defined various polynomials on the second cohomology, but essentially, if you just add up all those polynomials, you get a function on the second cohomology, which Kronheimer and Moravka proved under an assumption, which is true of all known Four-Manifolds, to be of this type with some rational numbers nx. And now I claim that in fact the nx's are the invariants that I've defined for you. Nx is just n of L, where x is essentially the first room class of L. So the relation of these invariants to the Donaldson invariants is given by this explicit formula. The generating functional of all the Donaldson invariants is simply this. I've written it this way to be as quick as possible. The way that most physicists would consider it more natural to also include the four-dimensional class. And then you get a more elaborate version of the formula that is more directly related to the physics and shows the appearance of two vacuum states, or two singularities, in what's sometimes called the U-plane, which I haven't mentioned today. But for saying as briefly as possible the relation to Donaldson theory, it's that the generating functional of all the Donaldson invariants is simply this for simple type, and a generalization of that can be worked out quite nicely for non-simple type. In short then, these invariants contain the same information as the Donaldson invariants. But is this formulation useful? Well, at this point, I'm definitely not the expert on that. There are definitely people here who know a lot more about it than I do. But we could look at simple imitations of two of Donaldson's basic early theorems to illustrate the fact that the formalism is useful. So one of Donaldson's early theorems is that his invariants vanish for a connected sum. If x is the connected sum of y and z have b2 plus positive, then the invariants of x vanish. And the second theorem was that on the other hand, the invariants are non-zero if x is scalar, with b2 plus bigger than 1. So combining them, scalar manifolds are not connected sums of this type. Well, we can actually imitate Donaldson's proofs, or imitate the first proof and simplify the second. As in Donaldson's case, to prove the first statement, you look at a metric in which y and z are connected by a long tube. The tube has the topology of a 3-sphere times r. Donaldson used the fact that the 3-sphere was simply connected. We'll use the fact that the 3-sphere has a metric of positive scalar curvature. And since positive scalar curvature tends to force the monopole field and everything else to vanish, you show that the solution, and in particular the monopole field, vanishes in this tube. On the other hand, using the topological condition on the two sides, you easily show that for a generic metric, there's no solution where m is non-zero, where m is 0 on either side. So m is non-zero on each side, but 0 in the middle. Now m being 0 means that in the middle the connection is reducible and has a gauge, there's a gauge transformation, namely a constant gauge transformation, that leaves m invariant. But it can't be extended to a symmetry on either side. So now, as in Donaldson's case where he used a similar technique, you make a gauge transformation on half the manifold. And that gives now a circle action on the space of solutions. It does nothing in the middle, so it's all right to do the transformation just on half. On one side it rotates m, it doesn't rotate m on the other side. This relative rotation of m on the two sides gives a free S1 action on the moduli space, quite similar to Donaldson's free SO3 action. So now in our problem, the moduli space is a zero-dimensional manifold that is a finite set of points with a free S1 action. So we're out of luck. It must be empty, and therefore with this kind of metric there aren't any solutions, and therefore the invariants vanish. Well, the second theorem we'd like to imitate is Donaldson's theorem, stating that the invariants are non-zero for scalar manifolds. Now, Donaldson proved that not by explicit computation, but by a kind of, well, not exactly an existence theorem, but by a kind of general theorem of ampleness and positivity in algebraic geometry. He showed that one of his invariants was the volume, in a suitable sense, of instanton moduli space, and therefore was positive, although not easy to calculate explicitly. Here one can be far more explicit and give a complete formula for the invariance of such manifolds. And via the relation to Donaldson theory, this also gives a complete formula for the Donaldson invariance of such manifolds. A complete but not rigorous formula, because the assertion that the two theories are equivalent is not yet rigorous, although Pitt-Sturgak and Turin may have made a big step in that direction. This complete formula for the invariance was obtained earlier, although not rigorously. At the beginning of my talk, I mentioned that determining the large T behavior of this theory was analogous to well-known unsolved problems. But I neglected to mention that in the Kähler case, there were results known even before my work with Seiberg, because I'd shown earlier that in the Kähler case, you could reduce the physics to another case whose large T behavior was known. So at a physical level of rigor, there already was a complete formula known for the Donaldson invariance of Kähler manifolds. And, of course, we recover the formula because all the physical arguments involve commute. In fact, the arguments in my original derivation of this formula were part of the elementary input in the work with Seiberg. So, I'll explain in a bit how to recover the formula, but of course, since the formula was already known, and moreover it was already known how to derive it, it was clear you could get the formula from the monopole equations. At the very worst, you could have simply imitated the arguments in my old paper. But upon going down that road a little bit, it turned out that it collapsed to something that could be explained much more directly. So what happens is simply that on a Kähler manifold, the spin bundle splits up as a sum of line bundles, where K is the canonical bundle. Of course, I'm writing this as if we had a spin structure so that K has a square root. Otherwise, we should be a little bit more precise, but let's not be right now. So since the spin manifold decomposes as a sum of line bundles, the monopole field can be decomposed into two pieces, which I call alpha and beta bar. I call one of them beta bar because it's beta that will turn out to vary holomorphically. And then the Witten formula, or in other words, the Lagrangian, turns out to have a very beautiful property, which, however, is obvious a priori from its relation to the Lorentz invariant supersymmetric field theory. Namely, when you write it out, the Witten formula, you see, this is something that you don't usually see in real life. We have the equations, a certain set of equations, A equals B equals 0, and there's a symmetry they don't have. But the symmetry they don't have is a symmetry of the Lagrangian, which means, in other words, that the same Lagrangian can be written as a sum of squares in more than one way. And by using the fact that the same Lagrangian is the sum of squares in more than one way, you get a very powerful vanishing theorem. So the point is that the Witten formula has a symmetry where you change the sign of beta, but you don't change the sign of anything else. But on the other hand, that wasn't a symmetry of the equations. I didn't write the equations yet, I guess. Oh, here they are. Okay. See, if you write the equations, which we will do presently, this is not a symmetry of the equations, but it's a symmetry of the sum of the squares of the equations. So if you're given a solution of the equations, it does not look like this transformation would give you another solution, because that transformation is not a symmetry of the equations. However, this transformation is a symmetry of the sum of the squares of the equations. And as a solution of the equations is the same as the sum of squares, given a solution that is a 0, making the transformation which gives another 0, you get another solution. Well, if we write out what the equations are, you'll see why that's useful. On a Kähler manifold, we decompose the curvature in pieces of definite Hodge type. And then we decompose the equations in this fashion into pieces of type 2, 0, 0, 2, and 1, 1. And here's my assertion that, oh, and then there's an equation that's the Dirac equation written for Kähler manifolds. So, you see, we seem to be in trouble because being on a Kähler manifold will give us no benefit at all unless we can use complex geometry by having holomorphic structures around. And unless F20 and F02 vanish, the structures won't be holomorphic, and we simply won't gain by being on Kähler manifolds. And the equation doesn't appear to show that F02 vanishes. Likewise, the equation isn't apparently invariant under that funny symmetry from the last transparency. But you see, what I said was that because the sum of the squares have this symmetry, any solution is mapped to another solution by this transformation. And you see, the transformation changes the sign of the right-hand side. And the knowledge that that gives another solution means that the right-hand side separately. Everything collapses. So the left and right-hand sides vanishing tells you that alpha beta vanishes, so alpha or beta is 0. And therefore F20 and its complex conjugate F02 is 0. So the structures are holomorphic. And then the Dirac equation, if alpha or beta is 0, the Dirac equation tells you that the other one is holomorphic. So now you have what you wanted. You've reduced to a holomorphic line bundle and a holomorphic section of another line bundle, plus a stability condition, which comes from the last equation. And now you have standard linear data, and it's obvious that the result can be worked out in principle. And you can even make it completely explicit in terms of geometric properties of the canonical divisor. So, I won't write it for you because I think that, although the steps are simple, it would be useful to squash into a brief through that I could give in a couple of minutes. But you get in a completely, well, you get in what I can assure you, having done it, in a completely elementary fashion, is a totally explicit formula. Before I go on, are there any questions? Yes?
So there's a slightly confusing point with respect to the symmetry of the Lagrangian. So the assertion is not that any solution is actually of the form either alpha or beta vanishes, but actually that simply you get cancellation in counting solutions that way.
If we were doing solutions of the second order equation, now you see, if we have a Lagrangian, we could take its Euler Lagrange equations. We get second order equations that have the monopole equations as a first order specialization. So the second order equations, all we could say is that beta goes to minus beta would be an obvious symmetry of the second order equations. But for the first order equations, we can make a much sharper statement. For general Four-Manifold, there was only one way to write the Lagrangian as a sum of squares. But on a Kähler manifold, there were different ways to do that. And, well, the symmetry isn't a manifest symmetry. The symmetry isn't a symmetry of the equations, but it maps solutions to solutions. And then, it follows from one of the snazziest things in contemporary theoretical physics, namely S-duality of n equals 4 super Yang-Mills, that if you form the generating functional of these numbers, that is, remember that AK was the Euler characteristic of the moduli space. If you take these numbers AK and use them to build up a formal power series, it follows from S-duality that this formal power series should be a modular function. In fact, Vafa and I were much more precise about what kind of modular function it is. And this assertion, although certainly not a theorem even at a physical level of rigor, is a consequence, first of all, of S-duality, for which there is enormous evidence. And secondly, it's been checked for lots and lots of Four-Manifolds. For instance, by now it's been checked for elliptic surfaces, and it's been shown that if it's true for a minimal Kähler manifold, then it's true for all its blow-ups. Those assertions are mostly due to Yoshioka. Well, I mean, I offer this, first of all, to point out that, you know, there's more to four-dimensional gauge theory than four-manifold invariance. I can't tell you what implications this will have in the mathematical world, but this appearance of modular forms given a four-manifold and a semi-simple E group, I hope you'll accept as a rather beautiful bit of mathematics, to the extent that it becomes mathematics. So I offer it, first of all, just a hint of some of the things that are over the next ridge in the world of gauge theories. And secondly, to point out to you that many of those ridges and valleys that lie beyond the ridges really involve studying the quantum theories and not just the classical theories. I couldn't resist mentioning this modularity at the end because I didn't want to leave you with the feeling that what we're discussing is a closed story that can be studied in isolation by looking at the classical monopole equations independent of the quantum field theory from which they came. Of course, that's true about if all you care about in life is, perhaps it's true if all you care about in life is the invariance of four-manifolds. But if you have a somewhat broader view of the mathematics, the geometry of gauge theories on four-manifolds and its connection with other areas of mathematics, then you shouldn't be content to treat every peculiar thing that physicists toss in your direction. As another comet that flew in from the Oort belt, or whatever it is, far beyond the orbit of Pluto, and is independent of all the others. There is that Oort belt out there which they're coming from, and in this case it's known as quantum field theory. I can't really explain this now, but even though, as bits of classical mathematics, the modularity of the generating functional and the equivalence of Donaldson theory to the monopole equations may sound like totally different stories, they in fact have a common origin in these duality symmetries of non-abelian quantum field theories. And at that level, they have a common origin also with other phenomena of recent interest, such as mirror symmetry in 2 dimensions, which again is a phenomenon that comes from the same neck of the woods. Nonlinear duality symmetries in quantum field theory. Thank you. Yes? Well, what I said was that it naturally is a sum of 2 terms. And the reason there are 2 terms is that in Donaldson theory there are these 2-dimensional classes. Okay. So you take a 2-dimensional class, take a 4-dimensional class. Of course, 4-dimensional cohomology classes on a 4-manifold are all. There's only one of them, it's a point. Then the Donaldson invariant is really a function of both of these. It's something like the expression isn't manifestly real. There's an exponent which is power of I, and there's a topological formula, the Wu formula, by which you show that it's real. So if you wrote one knows a generating function of all the Donaldson invariants, including the 2- and 4-dimensional classes, you get a bigger thing, which is really a sum of 2 terms. And the 2 terms, in the story I explained on Wednesday, there was this U-plane that parameterized a family of elliptic curves. And the elliptic curves degenerated 2 points. And the 2 terms are the contributions of the 2 singularities. And by the way, a lot of this is getting to be understood from higher groups like SUN. So for SUN, we have not the U-plane, but not one complex variable U, but n minus 1 of them. And they parameterize the family of hyperelliptic curves. And these are points where the hyperelliptic curves develop a certain kind of singularity. And for SUN, there are n of those points. And then the analog of this formula for SUN will be a sum of n times. N in general is the dual Coxer range of the BC. For E8, there are going to be 30 such terms in all these. Any other questions?
Thank you very much.